Welcome all in this lecture of quantum mechanics. The lecture is about Heisenberg's uncertainty principle, and this lecture will be discussed from the textbook Quantum Mechanics, a textbook for undergraduates by MC Jain. So let us start the lecture. In classical mechanics, we have learned that the position and the momentum of a particle are independent of each other and they can be simultaneously measured with precision. However, in quantum mechanics, a particle is represented by a wave packet. We know that if wave packet is expressed in terms of position, then it should have a varying amplitude. That is, amplitude is varying with respect to the position x. The particle may be found anywhere within the region where the amplitude of the wave function psi x is non-zero. So let us look at the structure of the wave packet again. This is the structure of the wave packet. I already told that it has a varying amplitude. So where the amplitude is non-zero, the particle can be found anywhere in this region. This is the region and the particle can be found anywhere. It should also be noted that the wave function can also be represented in terms of momentum amplitude function phi p. These were already discussed in our earlier lecture. The wave function can be represented in terms of position and wave function can also be represented in terms of momentum. So we can obtain wave packet for position and wave packet for momentum also. Now, in a similar way, we can tell that the momentum of the particle is indeterminate within the region where the momentum wave function phi p is non-zero. So, we can see that the position as well as momentum is indeterminate within the region of the wave packet. Now, an important question arises, that is how precisely we can determine the position and the momentum of a particle simultaneously. In order to answer this question, we have to recall the reciprocity relation that we have discussed in our earlier lecture. The relation was like that delta x into delta k greater than equal to 1. Now we know that p equal to h cut k, then delta p is equal to delta k into h cut. So if we put the value of delta k from this equation to this reciprocity relation, then we will obtain delta x into delta p greater than equal to h cut. This is known as Heisenberg's uncertainty relation for position and momentum. And it states that it is not possible to specify both the position and the momentum of a particle simultaneously with arbitrary precision. The product of the uncertainties in the position and the momentum is always greater than a quantity of order h cut. Later, we will obtain the exact statement of the uncertainty relation. This will be delta x into delta p greater than equal to h cut by 2. But right now, let us tell that delta x into delta p greater than equal to h cut. Now, this relation can be extended to 3 dimensions as follows. That is, if we consider the different components of x and p, then it can be written in this fashion. That is, delta x delta px greater than equal to h cut, delta y delta py greater than equal to h cut, delta z delta pz greater than equal to h cut. It is important to note that there is no uncertainty relation between one Cartesian component of the position vector of a particle and a different Cartesian components of the momentum. That means it will not be like delta x delta py greater than equal to h cut or delta y delta px greater than equal to h cut. The restriction are only on the complementary pairs, that is delta x delta px. If it is delta y, then The other variable will be delta py. If it is delta z, then the other variable will be delta pz, like this. It is also important to note that the uncertainty relation does not place any restriction on the precision with which a position or a momentum measurement of a particle can be made. So, it cannot tell about the precision, degree of the precision of the position or momentum measurement. But once the system is known to have one of these quantities defined to within a precision epsilon, then the measurements of the other quantity subsequently will give values spread over a range greater than equal to h cut by epsilon. This means suppose you are measuring position and accuracy for the position measurement is epsilon. If this is epsilon, then accuracy for the other variable, that is for the case of momentum, that will be greater than equal to h cut by epsilon. So the uncertainty principle cannot tell you the degree of the precision. If we know the precision of the one quantity, then we can specify the precision of the other quantity. Thus, more precisely one of the quantities is known, the greater is the range of values that will be obtained in a series of measurement of the other quantity. Like position momentum uncertainty relation, there is another uncertainty relation, that is energy time uncertainty relation. So let us derive this. E equal to p square by 2m. We know this relation. Now after differentiating, delta E is equal to 2p delta p by 2m. This gives us p by m delta p is equal to v into delta p. P is the velocity. Now we know another relation, that is t is equal to x by v. So if t is equal to x by v, then delta t is equal to delta x by v. Now if we multiply these two equations, delta E is equal to v delta p and delta t is equal to delta x by v, then we will obtain delta E delta t is equal to v into delta p, delta x by v is equal to delta x into delta p greater than equal to h cut. So again delta E into delta t greater than equal to h cut. So this is the energy time uncertainty relation. It should be noted that this relation may also be deduced directly from the form of wave packet when it was expressed in terms of momentum that we just discussed earlier. Now this relation, that is energy time uncertainty relation, connects the uncertainty delta E in the determination of the energy of a system with the time interval delta t available for the energy determination. So what is delta E? Delta E is the uncertainty in the determination of the energy. And what is delta t? Delta t is the time interval available for the determination of the energy. In quantum mechanics, it implies that a state of finite duration cannot have a precisely defined energy. This line is very important, that a state of finite duration, if the duration of the state is finite, then there cannot be precisely defined energy. For example, if an excited atomic or nuclear state has a lifetime tau, its energy is uncertain by an amount at least of the order h cut by tau. For the energy of a quantum state to be precisely defined, it must have infinite lifetime. Again, you listen this line. For the energy of a quantum state to be precisely defined, if we want to state the energy of a quantum state in a precise manner, then this state should have infinite lifetime. So this formulation was stated by Heisenberg in 1927, and the statement is that it is impossible to simultaneously specify the precise values of both members of certain pairs of dynamical variables of a system. These variables, called complementary variables, are canonically conjugate to each other in the classical Hamiltonian sense. The product of the uncertainties in the values of the two variables is at least of the order of h cut. So here we have learned about the terms complementary variables. What are complementary variables? For example, the uncertainty principle just discussed tells that delta x delta p greater than or equal to h cut. So x and p, they are actually complementary variable. Similarly, energy time uncertainty principle, energy and time, they are complementary variable, and these variables are canonically conjugate to each other in the classical Hamiltonian sense. In classical mechanics, we have learned the term canonically conjugate variable. So these variables are actually canonically conjugate variable, like xpx, ypy, zpz. Similarly, the j and phi, that is, angular momentum is j and phi is the angular position. These variables are also canonically conjugate to each other. It must be kept in mind that the limitations on measurement imposed by the uncertainty principle have nothing to do with the experimental errors that occur in actual measurement. So suppose you are measuring thickness of a foil by screw gauge. This is actual measurement. But uncertainty principle have nothing to do with the experimental errors in actual measurement. Further, the smallness of h cut ensures that the uncertainty principle is relevant only for systems of atomic dimension. So this principle is valid only in the case of atomic dimension, and the real experimental errors that occur in actual measurements, that has no relation with the uncertainty principle, and no results of classical mechanics are affected for macroscopic bodies. So these things we have to keep in mind when we will tell about the uncertainty principle. Now we will describe some experiments which help us to understand more clearly how the process of measurement creates uncertainties which are in accordance with Heisenberg's uncertainty principle. So I will discuss some of the experiments. The first experiment is Heisenberg's gamma ray microscope experiment. This experiment is actually a thought experiment. It means that it is an imaginary experiment which is consistent with the laws of physics but is not possible to carry out in actual practice. So this is the experimental setup. This experiment attempts to determine the position of an electron by observing it through a microscope. This small dot is the electron, and this portion is a part of the microscope. This is the lens of the microscope. So we are trying to observe this electron with a microscope. Now the initial momentum of the electron is known precisely. For simplicity, we assume it to be rest initially. So the initial momentum is known precisely. In order to observe the electron, it must be illuminated by radiation which is scattered by the electron into the microscope. So it means that there should be an incident photon, and this photon will be scattered by the electron, and this photon must enter into the lens of the microscope. If it does not enter, then we are not able to see the electron. So it must enter into the lens of the electron after the scattering. Now, if lambda is the wavelength of the scattered radiation, then the x component of the electron position cannot be determined to a precision greater than the limit of resolution of a microscope. We know that for every microscope there is a resolution. The theoretical resolution, the expression of the theoretical resolution of the microscope is lambda by 2 sin theta. where lambda is the wavelength of the scattered radiation and theta is this angle is theta. If this is the incident photon and if this is the perpendicular from the electron to the lens, then this angle is theta. So the theoretical formula of the resolution is lambda by 2 sin theta. And we are saying that the x component of the electron position cannot be determined to a precision greater than the limit of resolution of the microscope. That is, we cannot measure the x component of the electron position which is greater than the resolution. This is the resolution. So delta x, that is uncertainty in the position, will be of the order of the resolution. The resolution is how much? That is lambda by 2 sin theta. Theta is the half angle subtended by the lens at the electron position. This is the uncertainty in the position of the electron. Now, from the expression, it is very clear that smaller the wavelength of the illuminating radiation, if you make lambda small, then delta x will be small. If delta x is small, that is if the uncertainty is the small, then we can measure the position very accurately because we are decreasing the uncertainty delta x. Similarly, another thing we can do, that is delta x can also be decreased by increasing theta. We can increase the theta. If we increase the denominator, then what will happen? This term will decrease and uncertainty will also be decreased. So if we make lambda smaller, that is the first case, then we have to use wavelength of very small value. So what we have to do, we have to use gamma ray because we know that in case of gamma ray, the wavelength is very small. So we have to use gamma ray microscope. And if we want to make theta higher, then what we have to do? We have to use a lens of high aperture. So in this way, we can decrease the values of the uncertainty in position. Now, in order that the electron be observed, at least one of the incident photons must be scattered by the electron into the microscope. This Compton scattering imparts to the electron a recoil momentum because it must impart a recoil momentum because photon is scattered from the electron. So it will impart a recoil momentum to the electron. Electron will suffer this recoil phenomena. So what will be the value of the momentum? If the photon momentum is h by lambda, so the recoil momentum will be also the same according to the Newton's third law. However, the direction in which the photon is scattered cannot be known exactly because it can be scattered anywhere within the aperture of the lens. From the figure, if the value of the momentum is h by lambda, we know the value of the momentum is h by lambda from the de Broglie's hypothesis. So from the figure, the x component of the momentum of the scattered photon ranges from minus h by lambda sin theta to plus h by lambda sin theta. Let us look at the figure again. So suppose photon is going to this way, or photon can go through this way so that it enters into the lens of the microscope. So if you consider this direction, so it has a x component, actually it is in the minus x direction. So if this is the photon momentum direction, so this will be minus h by lambda sin theta, and in this direction it will be plus h by lambda sin theta. So this is the range of the photon momentum, this one. So uncertainty in the x component of the recoil momentum, if we add them up, so this will give, that is total uncertainty in the momentum delta px of the order of 2 into h by lambda sin theta. We are adding this one h by lambda sin theta minus of minus h by lambda sin theta. So delta px equal to 2 into h by lambda into sin theta. Note that delta px can be reduced by increasing lambda or decreasing theta. You just see the expression again. That is how to decrease delta p. You can decrease delta p by decreasing theta or increasing lambda. But the surprising thing is that both this procedure is just opposite to the procedure that we discussed in case of position. Px can be reduced by increasing lambda or decreasing theta. Just the opposite thing of this case, that is in case of delta x. In case of delta x, to reduce the uncertainty in the position, what we have done, we have to reduce the wavelength and we have to increase the theta. But to reduce the uncertainty of momentum, what we have to do, we have to reduce the delta p by increasing lambda, increasing the wavelength and decreasing the theta. So the opposite thing. So the point is that we cannot reduce both delta p and delta e simultaneously. So there must be some uncertainty for simultaneous measurement of the position and momentum. And if we multiply the two expression for the uncertainty, that is delta x and the uncertainty delta p, then after multiplication it will give us delta x into delta p of the order of h, and which is consistent with the Heisenberg's uncertainty principle. So this is experimentally verified. Another experiment may be discussed, that is double slit interference experiment that we have discussed earlier lectures. So this is the setup. This is the source of the electrons. There are two slits A and B, and this is the screen. This is capital D, the distance between the screen and the slits, and distance between the slits A and B is small d. M is a microscope. So what is our aim? We are employing a microscope to detect that through which slit an electron goes through. We are employing a detector to detect through which slit the electron passes through. Now, the distance between the slit is small d, that I have already told, and distance between the slit and screen is capital D. The distance between successive maxima on the screen would be beta equal to lambda into capital D by D. This expression we have learned from the Young's double slit experiment, that distance between the successive maxima on the screen is beta is equal to, that is fringe width is equal to lambda capital D by small d. We know the expression. Lambda is the de Broglie wavelength in case of electron, and lambda is equal to h by p. We also know that in case of electron, expression for the lambda will be given by the de Broglie's hypothesis, lambda is equal to h by p. The detector is placed just behind the slits. It is a microscope along with a illuminating device, in order that the microscope tells which slit the electron came through. It should measure the y component of the electron's position to a precision better than half the distance between the slits. So listen very carefully. This microscope can tell us that through which slit the electron came through. So this microscope should have a precision. But how much precision it should have? So you see in the experimental setup that suppose if the electron passes through this slit A, so from this baseline the distance is d by 2. So at least this microscope should detect this position, the value of this position d by 2. This should be the minimum value of the accuracy. Otherwise the microscope cannot detect that through which slit electron passes through. That is why they are saying that delta y, that is uncertainty in the position of the electron, delta y, that should be less than d by 2. Delta y less than d by 2. In order to detect the electron, an illumination photon must bounce off the electron into the microscope. That means that microscope, that is, there should be a photon. That photon is striking the electron, and after striking it is being scattered from the electron and it is entering into the microscope. Because if it does not enter into the microscope, then we will not see the electron. This will impart to the electron a momentum in the y direction and thereby introduce an uncertainty delta p in the y component of the electron's momentum. Just like the previous experiment, it will also impart a momentum to the electron, and uncertainty in the momentum delta py, the y component, that should be greater than equal to h cut by delta y according to Heisenberg's uncertainty principle. If the uh, uh, positional uncertainty is delta y, then uncertainty in the momentum delta p, that should be greater than equal to h cut by delta y according to Heisenberg's uncertainty principle. Now delta y less than d by 2. So putting this value delta py greater than equal to 2h cut by d. So uh, there is a uh, deviation in the momentum, that is delta py. So what will be the angular deviation? Angular deviation is given by delta p by p. This is the angular deviation, delta p by p. So we are just putting the values p equal to h by lambda, delta p is equal to 2h cut by d. Ultimately this gives us lambda by pi into small d. So if this is the angular spread delta d, then what will happen when the electron will reach the screen? That is, here when the electron will reach the slit, so there will be a deviation in the position. That is, suppose electrons is going to strike there, but there should be a deviation in the position because of the recoil momentum of the electron. So if the angular spread is delta theta, then the uncertainty in the position delta y will be d into delta theta, because d is the linear distance, delta theta is the angular deviation. So uncertainty in the electron position delta y will be d into delta theta. So multiplying d, it gives us lambda into capital D by pi d. Now look at this expression very carefully. Lambda into capital D divided by pi into small d. So if we ignore the value of pi, this expression is almost same as the expression of the fringe width beta. Beta equal to lambda d by d. So according to uncertainty principle and as per the experimental results of the experiments, so we have get that uncertainty in the position of the electron in the screen will be of the order of the fringe width. You listen it very carefully. That is uncertainty of the electron reaching the screen, that is of the order of the fringe width. Now to get a interference pattern, there is some fringe width. Fringe width means that is the distance between the maxima. So to obtain a clear interference pattern, the maxima should be separated by a particular distance that we call as fringe width. But if there is uncertainty in the electron position which is comparable to the fringe width, then what will happen? Then the interference pattern disappears, because there is uncertainty in the position of the electron and the value of the uncertainty is of the order of fringe width. That means the fringe will not be formed clearly and interference pattern disappears. So what is the conclusion of the experiment? As we have tried to detect through which slit electrons are passing through and we have employed a microscope, so in that case interference pattern disappears. So actually this must have to happen, because we have discussed in the earlier lecture that if we try to detect through which slit electrons are passing through, then we will not get any interference pattern, because at that time electrons will behave as particles, not electrons will not behave as matter waves. So we will not obtain any interference pattern. Here also, as we have set up the arrangement to detect from which slit electrons are passing through, so we are not obtaining any interference pattern. So this fact is consistent with the uncertainty principle, and it also establishes the that is correctness of the uncertainty principle. So uncertainty principle proposed by Heisenberg must be true. Now there are several consequences of the uncertainty principle. That is, from the concept of uncertainty principle, we can predict several important useful results. There are several results, but in this lecture, I am going to discuss just one result in detail. Suppose we will measure the ground state energy and the radius of the hydrogen atom. Now, this is the energy of the electron for the hydrogen atom. This is kinetic energy P square by 2m. This one is the potential energy. Now, if we consider the atom of size r, then uncertainty in the position of the electron will be of the order of this size, that is delta r is of the order of the atomic dimension r. So if delta r equal to r, then the momentum p, that is of the order of delta p, that is uncertainty. Now what will be the value of the delta p? Delta p is of the order of h cut by r, because we know that is delta p delta x is of the order of h cut. So if delta r is of the order of r, then delta p will be h cut by r. Now if this is the value of the momentum, then by putting the value of the momentum in the expression of the energy, we obtain this one. This is the expression of the energy. Now the system will be in the state of lowest energy when d by dr is equal to 0. So this expression will give us a particular expression for the value of the radius. Now the important thing is to note that this expression is exactly the same expression that was obtained for the first Bohr radius A0, and the value of the A0 is 0.53 angstrom. So the uncertainty principle give us the correct value of the Bohr radius. Similarly, if we put the value of R in this expression of the energy, that is equation 5.35, then we obtain the value of energy E is equal to minus h cut square by 2m a0 square, and after putting all the values, it will give us the value of energy E is equal to minus 13.6 electron volt. So again, we are obtaining the energy of the first Bohr orbit. So by employing the uncertainty principle, we are obtaining the value of the radius and energy for the hydrogen atom. The important point to note is that total energy of an atom has a minimum value which is compatible with the uncertainty principle. It is also clear why atoms are stable and do not collapse. So from uncertainty principle, we can give us some estimation about some important quantities. Another thing is to note that when we walk along a floor, we do not fall. Why we do not fall? Because there is a friction. The frictional force is something that that helps us not to fall. As we walk, our shoes with their mass of atoms push against the floor with its mass of atoms. So shoes are pushing the floor with the mass of its atoms. In order to squash the atoms close together, the electrons would be confined to a smaller space. So when we are pushing the floor with our shoes, so electrons are confined to a smaller space, and by the uncertainty principle, their momenta would have to be high on the average, because delta x is low, so delta p should be high. If delta p should be high, it means that electrons have high energy. So with high energy electrons, the floor is also giving us a backward force, so that we are able to walk. The resistance to atomic compression is a quantum mechanical effect and not a classical effect. So Heisenberg's uncertainty principle has many applications. Similarly, we can also prove the non-existence of electron inside the nucleus. So the procedure is just like same as we have discussed earlier, and in the similar manner we can show that from the uncertainty principle the non-existence of electron inside the nucleus. I request the viewers to read this portion clearly from the book of MC Jain. Similarly, we can also estimate the zero-point energy of a harmonic oscillator from the Heisenberg's uncertainty principle. In the same way, we can also explain the broadening of spectral line. So there are several phenomena which can be explained from the concept of Heisenberg's uncertainty principle. And I want to thank you all for listening my lecture. Thank you again.